All right, here we go. So we're going to review ionization energy and electronegativity real quick, okay? And let's look up here at the periodic table. The trends for both ionization energy and electronegativity both perfectly coincide with the trends on the periodic table for atomic size or atomic radius, right? Go from here to here. These atoms right here have the highest ionization energy, and in this corner right here, you have the lowest ionization energy. Right here in this top corner, you have the highest electronegativity, and right here in this bottom corner, you have the lowest electronegativity. So let's talk about what those things mean. All right, first one, move us over here. Ionization. Ionization energy. Right? Can anybody tell me about this S? This S right here? I mentioned it yesterday. All right, that S is the English spelling. And then you'll see it written sometimes this with American English with a Z there. Doesn't matter, I don't care, all right? Ionization energy. All right, here we go. Here are two different atoms. Beep, boop, boop. And here's another one. Beep. All right? Now, one of these would have a much lower ionization energy than the other. There we go. Which one of these atoms do you think would be easier to steal an electron from? Drew? Correct. This electron right here will be much easier to steal than these electrons, okay? There are several reasons. One, this atom only has 3 protons. This atom has obviously 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 protons, right? So this atom has a much weaker nucleus, much weaker electromagnetic pull than this atom. Reason number 2, which is a huge deal, look how far away that electron is from the nucleus, and look how close these are, right? So just like you know that magnets have to be close together to work, it's the same thing with the attraction between protons and electrons. So a big atom like this has a low ionization energy, and a small atom like this has a high ionization energy, okay? That's the biggest thing. Now watch. Let me draw you an atom that would have a really, really, really low ionization energy, and here it is. Look at that guy right there. This guy would have a very, very super low ionization energy. The energy required to steal this electron would be very, very low. There's 2 reasons. Reason number 1, look how far away this electron is from the protons. That's reason number 1. Reason number 2, all of these other electrons are in the way. So the negative electron is attracted to the positive protons in the nucleus. But also, all of these electrons are repelling it because like charges repel, correct? So this process or this phenomenon where these other electrons get in the way is called electron shielding. And we talked about that in yesterday's lesson. These guys are getting in the way of this guy being attracted to the nucleus, right? So this is an atom. This is rubidium. And you can see where rubidium is on the periodic table. We're getting down here And cesium would be weaker, and francium would be even weaker than that, right? So now, let's watch an atom undergo different ionizations, okay? We're going to ionize an atom, okay? We're going to run it through multiple ionizations. Let's come up with somebody here. How about 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Everybody, this is magnesium, right? Everybody agree with that? All right. Magnesium has a fairly low ionization energy. It only has 2 valence electrons out here. The more valence electrons you have, the harder it is for someone to take one from you, okay? Because the more valence electrons you have, the smaller your atom's getting. All right. Magnesium. This is magnesium. If this atom were ionized, if another atom came by and stole that electron, then after the first ionization, we would be looking at an atom that actually looked like sodium, but it would really be magnesium plus 1. After the first ionization, magnesium plus 1 will be a smaller atom than magnesium. The reason is this atom still has all 12 protons in the nucleus, but now it only has 11 electrons. So the electromagnetic pull on each electron is stronger. Does that make sense? This atom can and almost always would be ionized yet again. What if another atom that was a very strong magnet came by and stole this electron? Okay? Whoop. Then this thing would shrink. It would lose this whole outer shell. And you would have magnesium plus 2 because now 2 electrons are missing. This would be the second ionization. And the second ionization would result in a huge change in size because we've lost this entire ring. So magnesium plus 2, can you tell me what Bohr model magnesium plus 2 would look just like what? Neon. It would look exactly like neon, except for it would be smaller. Does that make sense to everybody? Okay, so now we've talked about ionization energy, and we've talked about first and second ionizations, and what each different ion looks like. So that's going pretty quick, right? And now we're going to talk about the opposite. We're going to talk about electronegativity. If we look up here at the periodic table again, the most electronegative atoms are, well, not these guys at all. Why are these guys, Sullivan, why are these not electronegative at all? Let me rephrase the question for you. Why do these guys not want to steal electrons from anyone? Exactly right, because they're already full. So they don't even count. So the very strongest magnet on the periodic table is fluorine. It's very, very small, and it only needs one more electron. So let's draw fluorine, and let's think about why it is so electronegative. Okay? Electronegativity. Electronegativity is basically how strong a magnet you are. I'm going to draw fluorine. Fluorine is 2 and 7. There are many things that make fluorine very, very strong. One, it's very small, so that's good. It has a very small atomic radius. That's how we describe the size of an atom. The radius, the distance from the nucleus to the outside of the atom, right? So fluorine has a very small atomic radius, all right? Now let me draw another atom beside of fluorine. Let me draw sodium. Okay? This is not a bad picture. I know it might look ridiculous to somebody, but it's not bad. If you look, here are the protons for sodium. Here are the protons for fluorine. Now, think about this electron right here. It's actually, when these two atoms get close to each other, this electron is actually closer to the nucleus of fluorine, isn't it? Does that make sense? And fluorine is very electronegative, has a very strong electromagnetic pull. So this electron, scoop, ends up right here. And now you have fluorine -1. And now you have sodium, it just lost that electron, sodium +1. Sodium obviously, skidook, shrinks a lot, and then fluorine inflates a little bit. Why does fluorine, Zach, tell me, why does fluorine's outer circle get a little bit bigger than it was before? It's got one more electron, but it still only has the 9 protons. So each one of these electrons doesn't have quite as much pull towards the nucleus. Okay? So fluorine is very electronegative. Okay? I'll draw you another atom, and you tell me if it's more or less electronegative than fluorine. All right, this is chlorine. Do you think, Maisie, do you think this would be more or less electronegative than fluorine? Less, that's right. And for those of you at home, what she did was she looked here and she said, well, if fluorine is the very strongest one, then chlorine's got to be a little weaker. Bromine would be a little weaker. Iodine would be a little weaker. Astatine would be a little weaker, right? So fluorine is the strongest one. So chlorine is a little bit weaker, doesn't have quite the electronegativity. And let me ask you, because I'm almost done, let me ask you, why? Why is this fluorine, why is this one stronger than this one? What do you think, Sullivan? Why is this one stronger than this one? Yes, it is smaller, and therefore you can get closer to the nucleus. Does that make sense? The radius here and the distance to these positives is less than the distance to those positives in there. So this is more electronegative. So if I was going to make a little thing for strength, this one is stronger than this one. All right, I think that's our review of electronegativity and ionization energy. There's a worksheet that goes with this.